materials for overall electrochemical water splitting. So I'm based in Brisbane, Australia at QUT, so there's a picture of our campus down here at the bottom. So if anyone is interested in visiting, it's a nice part of the world to come and visit. So in terms of the motivation of why we're doing this, so if we're looking at global energy consumption, we can see that we have a rapid energy demand globally. And if we look at the energy mix that's used to feed that demand, then you can see that it's dominated by fossil fuels. So given that, we have a significant CO2 footprint in terms of our energy sources. So ideally, we would like to replace that renewable energy, certainly with the sun and the wind. And being based in Australia, we certainly have a lot of sun and we have good wind, so we definitely want to take advantage of that renewable energy source. But one of the biggest problems is how do we store the excess renewable electricity that we generate? And that brings us on to this overall concept of what's been termed by Bockers in the 70s as the hydrogen economy, but we're transitioning more towards a hydrogen society, or that's what we envision. So we can see here that we still have fossil fuels dominating our current mix, but we can hopefully transition that into a hydrogen society, which is based upon the electrification of industry. So again, renewable energy, electrifying industry, to make that a green process. Hydrogen can come into that in terms of using fuel cells to make electricity. We can use it for transport. And as I said, storing chemically a lot of excess renewable electricity that we can generate, certainly in countries like Australia where we have the potential to generate a lot. So again, this is all based on making green hydrogen as opposed to hydrogen from any other source that is fossil fuel based. So in terms of hydrogen at the moment, in terms of global use, ammonia production, that's one of the main users of hydrogen. Metal processing is another industry that uses it a lot. But again, if we can transition industry to using electricity and also using hydrogen to power their processes, then we can again clean up our energy systems. So that's the goal of this particular type of research. So one of the things that we're doing at QUT at the moment is we're building a pilot plant facility where we're looking at kind of a plug and play technology scheme where we can integrate concentrated photovoltaics, silicon photovoltaics with electrolyzers, fuel cells and batteries, and then base that all on a DC microgrid. Water is also a concern, certainly here in Australia. So we're going to have water treatment plants in terms of taking seawater and desalinating that so that it's appropriate for use in electrolyzers. So this is the kind of plant that we have envisioned and is being commissioned at the moment. So delving a little bit more into those electrochemical applications, we're going to have different types of electrolyzers and different types of fuel cells. So at the moment we're going to be based on the alkaline electrolysis and PEM electrolysis, and also start to look at some solid oxide fuel cell work. So again, having this integrated approach to different technologies to plug and play and see how they interact with each other. So we think that's going to be very important of basically how you can build a plant like this that has balanced plant and can integrate seamlessly with each other to get the maximum benefit from each of these particular technologies. Okay, so this talk is mostly based on electrolysis to produce green hydrogen using renewable electricity sources. So if you look at the literature, it's dominated by transition metal materials. So they may be oxides, there might be phosphides or chalcogenides. And one of the main questions that we wanted to ask is, can we use abundant materials that exist already and convert them into electrocatalysts to use for green hydrogen production? Because we have to remember that if we do want to transition, the scale at which we have to do this is extremely large. So if we can use abundant materials that we have already, even better. So a lot of you are probably familiar with this diagram. So here we basically looking at overall water splitting. So on this end we have the oxygen evolution reaction where we generate oxygen, and on this side we have the hydrogen evolution reaction which we generate hydrogen. So when we do overall water splitting, we can't generate hydrogen unless we generate oxygen as well. And there's a lot of terms here in terms of the overpotential associated with each of those processes on how efficient our water splitting is going to be. So the basic aim here is to reduce these overpotential values close to their thermodynamic limit and to basically get as much current as we can out of our catalytic process. So that's the aim when we're developing these particular catalysts, and also to make them stable with time. So one of the approaches that we have, as I said, we want to have a sustainable approach. So we looked at recovering materials from spent batteries. So the zinc carbon battery is based on the Leclanche cell. So that uses zinc and manganese dioxide as the anode and cathode in that particular battery. And when you look at the amount of waste that's constituted in landfill by these batteries, it's quite a lot. So a lot of these batteries do end up in landfill. So if we can recycle these batteries and make them into something useful, that has another benefit for the environment. So one of the processes that we did was we removed the battery material, and then we did a pyrolysis process. And what we end up, by varying the temperature and the atmosphere that's involved, we end up with a manganese oxide type material. So the composition that we got was manganese 3O4 as opposed to straight manganese dioxide. So we characterized this one with Raman and XRD to confirm the composition, and we can show that the initial material had carbon in it, but after we treat it, we don't have any carbon left. So we have a pure manganese oxide material. In terms of its performance, it was reasonably good. So compared to commercial manganese dioxide, it was better in terms of the current density that we're passing. And the impedance was lower during oxygen evolution. And the most important part is that the stability was a lot better. So for the commercial material, it started to degrade over a 24-hour period. So if we look at some of the TEM images before and after we do that particular reaction, we can see here we have the phases due to the manganese 3O4 material. And we can see that after oxygen evolution, the composition remains the same, but we are starting to generate some amorphous material at the surface of the crystalline particles that we're using on our catalyst. So what we're thinking is happening here is that the surface of the materials is becoming amorphous, which is giving us our high activity, because there's a lot of evidence now in the literature that amorphous materials are more active than their crystalline counterparts. Another example that we looked at is iron ore. So that's something we mine a lot in Australia, and we do export a lot of it to other countries. So one of the motivations that we have here is that can we value add to that iron ore. So basically use this as a valuable material in water electrolysis. So the type of iron ore that we had here consists of these particular phases in the iron ore. So what you'll notice is that we have obviously a lot of iron, but we also have nickel in there, which is a known catalyst for oxygen evolution and also hydrogen evolution. So we thought, okay, we have a lot of ingredients here, which could make this an active catalyst for both reactions. So when we tested it, we can see that yes, we do have quite good oxygen evolution activity. So our current density is pretty high. We're getting up to about 250 milliamps per square centimeter, which is pretty good. And we also have hydrogen evolution activity as well. Not as impressive as other materials in the literature, but it was certainly promising that we could get hydrogen evolution from this raw material as well. So if we look at the oxygen evolution voltage that we get and the hydrogen evolution voltage, you can see that for a 2-electrode cell, we don't have to operate it at too high a voltage to get overall water splitting. And we can see that the taper slopes are quite reasonable as well for both of these particular reactions. One thing we did notice is that if we do perform the oxygen evolution reaction and then we wanted to use that same material for hydrogen evolution, there was a real drop-off in activity. So here this is the pristine material, and then if we do oxygen evolution, we can see there's a major decrease in the activity. So we're trying to understand why running it in the oxygen evolution region causes such a detrimental impact on the hydrogen evolution reaction. So if we look at the TEM, before and after. So before, we have quite a dense material, and we can see the phases associated with an iron nickel sulfide species. And after the oxygen evolution reaction, it becomes more porous, and it actually becomes more crystalline, and we start developing newer phases of the iron nickel sulfide. So for some reason, that is good for oxygen evolution performance, but not for the hydrogen evolution reaction. So we had to understand why that was the case. And what we found was that we're losing actually a lot of sulfur from our material. So when we did our oxygen evolution reaction, the sulfur was being oxidized into the sulfate, basically being lost from solution. So then this nice metal sulfide material was no longer available at the surface to perform the hydrogen evolution reaction. So that leaching of the sulfur really impacted on our hydrogen evolution reaction performance. And that raises the concept of what we call bifunctional electrodes. So this has been discussed a lot in the literature, where people report a material which is active for the oxygen evolution reaction and the hydrogen evolution reaction. And basically these are based on metal phosphides, sulfides and selenides. And usually the metals involved are iron, nickel or cobalt. So then the question is, could these be suitable for deployment in commercial electrolyzers if phenomena like this were actually happening? And there's two key papers that came out a few years ago, which actually looked at commercial electrolyzers and basically what happens to them when you turn them on and off. And there was a surprising finding here, is that when you shut down an electrolyzer, you actually get reverse current flow occurring in your electrolyzer. So basically your anode becomes your cathode and your cathode becomes your anode. And certainly with your cathode being oxidized, that causes a significant problem. So as we saw in that example, when we used our iron ore, when we oxidized it, it was very detrimental to the hydrogen evolution reaction. So this raises the question, okay, if we use these metal calcigenide species as a bifunctional catalyst, is it really bifunctional? So we did a case study based on nickel, nickel sulfide, nickel phosphide, and nickel selenide. So we can see the oxygen evolution reaction for the phosphide and the selenide actually improves with the number of cycles, whereas you can see there's a dramatic decrease in the hydrogen evolution reaction after you do oxygen evolution. So you're getting a real compromise in activity if you allow your cathode to be oxidized in any way. So if this was plugged directly into a solar cell, and when the sun doesn't shine anymore, when your electrolyzer turns off, you're into that reverse current regime, which would then be detrimental to your cathode. So we can see here from the impedance spectrum. So for the oxygen evolution reaction, we actually got a decrease in impedance. So that's telling us that our oxygen evolution reaction performance was getting better. But you can see for the hydrogen evolution reaction, the impedance went significantly up in all cases for the sulfide, the phosphide, and the selenide. So any oxidation of that cathode is very detrimental to the hydrogen evolution reaction, and certainly increases the overall impedance of that particular system. We looked at it in a 2-electrode configuration as what you'd get in a commercial electrolyzer. So you can see that when we're operating each of these as is, so we're keeping the anode and the cathode performing for this period of time, we can see that we have steady potentials over that period of time when we operate it correctly. But then if we switch electrodes, or actually turn it off and then turn it back on again, we can see that the voltage goes right up for all of these materials. So again, that's being influenced by the chemistry that's happening at the cathode if it's allowed to be oxidized. So you can see here it has quite a detrimental impact on the overall cell potential if we allow that to happen. So the question is, what's actually happening to that material? So we looked at the nickel phosphide in this particular example here on the slide, but if you go to the paper, you can see the analysis on the other materials. But basically what happens in this particular case, after we do a little bit of oxygen evolution, you can see that the phosphide is no longer a phosphide, but it actually becomes a phosphate. So that oxidation at the surface really destroys the metal phosphide bond to create metal phosphates at the surface, which are known to be not very active for the hydrogen evolution reaction. So basically, this chemical change that's occurring at the surface of our catalyst is very detrimental to that overall performance. So it's something to be aware of if you're integrating materials like this in an electrolyzer that are going to be directly integrated with intermittent renewable energy sources. So the question is, we know we have a problem, so can we solve it? And again, we wanted to take a sustainable approach to this in terms of a readily available material that we can investigate. So a very well-known material is stainless steel. And why we chose stainless steel, I will explain that here. But just to put it into context, the amount of stainless steel that's being produced every year is increasing. So in 2018, it was up to 50.7 million metric tons of stainless steel. So this has been produced all over the world on a vast scale. And they expect the market to reach 133.84 billion US dollars by 2025. So the production of this material is certainly not going to cease anytime soon. And as you can imagine, in the production of stainless steel, there's going to be a lot of waste of stainless steel. So not all of it is going to be used for purpose. There's going to be, depending on how you machine it and cut it, there's going to be a lot of leftover steel to deal with. So if you look at the composition of steel, obviously iron makes up most of the material. But if we look in here, again, we have our nickel, which is an active catalyst, as I said, for oxygen evolution and hydrogen evolution. We also have manganese, as we saw in the first few slides, that is also active. And we have phosphorus and sulfur, which we know, if we have it as the phosphide or sulfide, is active for the hydrogen evolution reaction. And we also have some chromium in here. And there's been a few recent reports where people have doped metal oxides with chromium to improve corrosion resistance, but it also actually improves the electronic nature of the catalyst for the oxygen evolution reaction. So having chromium in here is also beneficial. So what we did was we did an electrochemical modification process. So we take stainless steel, we put it into 6 molar KOH, which is a normal electrolyte used in alkaline water electrolysis. And we can see here that if we cycle our potential, here we have a redox process associated with iron that's in the steel. Here we're getting a process due to nickel. And then we can see there's a rapid increase in current, which is due to our oxygen evolution reaction. So we can see here by electrochemically conditioning our material, here we go up to 150 cycles, is that we're getting really good oxygen evolution currents being developed at our catalyst. So what we did as a further step is that we introduced a little bit of gold into the solution, into the material as well, by a galvanic replacement process to dope some gold into our modified steel. And the reason for that I will explain in a minute. So if we look at some SEM images, so pristine steel, as you can imagine, it's relatively rough as it's polished. We didn't want to smooth it down too much. We took it as received. And then when we did our electrochemical treatment, we can see that we're getting these flake-like structures, which are highly indicative of double layer hydroxide type materials. And if we look at TM of that sample, after we've done our gold modification process, so again, we can see those nice flakes of the layered double hydroxide material, and then these little parts here are small gold nanoparticles distributed throughout that material. So again, our distribution of iron, chromium, nickel, and manganese is quite even across that sample, and then we have decoration of gold throughout our particular sample. And if we have the SAED pattern, we can index that to gold and also various phases of the iron-nickel hydroxide material. If we look at performance, so now we can see that our hydrogen evolution reaction, we're getting really high currents up to about 600 milliamps per square centimeter, and it's definitely outperforming platinum. Not in the onset potential, but certainly in the high current density regime, we're getting a lot better activity compared to commercial platinum. For the oxygen evolution reaction, we're also getting really high currents. So we're getting up to about 800 milliamps per square centimeter for the oxygen evolution reaction as well, which is quite good. So again, we can see that we have stability as well in terms of hydrogen evolution and oxygen evolution over a 20-hour period. So our material looks good. What we should note here is to get good hydrogen evolution activity, we needed the gold. If we didn't have those gold nanoparticles in there, then our activity wasn't as high. It was this S2 value here. So the addition of gold was really beneficial to promoting the hydrogen evolution reaction. If we look at the surface composition by XPS, we can see on the initial stainless steel, obviously we don't have any gold. Once we do our modification process, our gold comes to the surface. And then after we do oxygen evolution and hydrogen evolution, we don't see any change in the composition of our catalyst. So that's quite interesting. So what we saw in the slides before is that after we do the oxygen evolution reaction, we get significant compositional changes at the surface. Whereas here, for this particular sample, with the gold present and with the chromium present, it mitigates against severe oxidation of the species on the surface. And that bodes well for the type of experiment that we want to do next. So what we did with our 2 electrode setup, we can generate quite good current over a relatively good time period. But then what we did was to mimic turning on and off our electrolyzer, is that we ran it for a good 72 hours under normal conditions, and then we reversed the polarity. So the anode became the cathode and the cathode became the anode, and we don't see any degradation in performance. And then we switched it again after another 72-hour period, and again we can see that the performance stays the same. So we're excited by this one in terms of that the anode and the cathode, it doesn't matter what you actually do to them, they'll perform at the same level, even if you reverse the polarity of your electrolyzer. So this bodes well for direct integration with renewable electricity. And the other advantage is that we're only using 0.1 to 0.2 atomic percent of gold. So in terms of cost, this certainly won't blow out the cost of your catalyst, especially as we're using stainless steel, which is relatively cheap. So we're quite confident about this one, and we're looking to scale this into a 2 kilowatt electrolyzer, and then have that out at our pilot plant to see how it goes over weeks and months, and that's the coming research on that particular area. Okay, so just to finish up, so basically we covered 3 different areas in terms of using sustainable materials to generate catalysts that can split water. So we can use primary batteries that we can recycle and recover from landfill and to use as a catalyst. We can use iron ore, which is dug out of the ground here and cleaned up as a catalyst and without any further modification. And we can also use stainless steel, which is a readily available resource with a little bit of gold doping to make that tolerant to polarity switching for commercial applications. So hopefully I've given you an idea that we can use a lot of readily available materials out there for these type of advanced applications. So finally, I'd just like to thank the electrochemistry group. So Dr. Umul Sultana, who's here, and Dr. Abu Saeed did most of the work. Jixon, who's not pictured, did the work on the batteries. And some of this work was done in collaboration with UNSW in Sydney. And just like to thank the Australian Renewable Energy Agency and the Australian Research Council for funding. So thank you.